So I want to look at how we actually compute exponentials of matrices, and I'm going to do it with this example. What is the exponential of this matrix, 2 by 2 matrix? The answer should be some 2 by 2 matrix. So how can we do this? If we just use the definition directly, then, so let's call this matrix A. So let's say A is 1, 2, 2, minus 2. Then my question is, what is e to the A, right? Then the answer is that e to the A is the identity matrix plus A plus 1/2 A times A plus 1 over 3 factorial. So this was actually 2 factorial. This is 1 factorial, and so on. A cubed. And then find all of those and then figure out what that series converges to. Hopefully that is sounding like a horrible task for you, right? Even just this is really annoying to compute, right? And then it gets more annoying as you go along. Like A squared, that's this matrix times itself. That's quite complicated, right? That's not just like this term squared, that term squared. You're not just multiplying terms over, right? You have to actually do matrix multiplication. Everything's going to get intermingled and mixed in some complicated way. And each time that will happen, A cubed will be A times A times A, a triple matrix multiplication. It's super annoying to compute and just impractical. So using this definition, not so good. Not for this matrix, at least. But it works for certain matrices, it works well. There are certain matrices where if you try to square them, then it is really simple. Or if you try to cube them, then it is really simple. The diagonal matrices. So let's say I have a matrix like 5, 3 on the diagonal and then zeros there. Then what's its square? It turns out it is just this. You can just square the individual terms. That will fail horribly if you didn't have 0 here and here. But when it's diagonal, when you do have 0 else off the diagonal, this works very nicely. And it continues to work for all powers. So if you want this to the nth power, then that's just this. So then, what happens if you want e to this diagonal matrix? That you can handle using the power series directly. So that should be I plus this matrix. So I is just 1, 0, 0, 1, right? Let me just write that out. 1, 0, 0, 1 plus this matrix plus 1/2 that matrix squared, and so on. 1/3 that matrix cubed, and so on. And we're in a situation where the matrix is diagonal, so squaring the matrix is just a matter of squaring the diagonal entries. Again, that absolutely does not work for a non-diagonal matrix like 1, 2, 2, minus 2 that we're starting with here. That works for this one. It's diagonal. So then look at the individual entries here. So adding matrices is just a matter of adding the terms, right? Adding matrices is very simple. It's multiplying that's usually complicated. So adding is just adding the terms. So here we have 1 plus 5 plus 5 squared times 1/2 plus, you can tell what the next term is going to be, right? 1 over 3 factorial, 5 cubed, and so on. Because each time you take one of these diagonal matrices to a power, the powers just end up on the diagonal, on the terms, on the entries of the matrix. So that is the top left entry there. And then the top right entry is 0 plus 0 plus 0, etc. So it's just a bunch of zeros. And then the bottom left entry is a bunch of zeros. And the bottom right entry, you can see, is 1 plus 3 plus 1/2 3 squared, and so on. So the top left and bottom right entries are these infinite sums. And these infinite sums are actually just ways of writing. This one is e to the 5, and the infinite sum down there is e to the 3. You see? So look what we have discovered. It doesn't really matter that these numbers were 5 and 3. What mattered is just that the matrix is diagonal. E to a diagonal matrix is something you can compute very easily. It's just the matrix whose another diagonal matrix with the individual entries on the diagonal exponentiated. So to exponentiate a diagonal matrix, just exponentiate the entries along the diagonal. Don't exponentiate all entries. Notice I did not exponentiate the zeros, right? Like, if I did, then you would have seen 1 show up here. E to the 0 is 1. No, don't exponentiate those. For a diagonal matrix, you can exponentiate the terms on the diagonal to exponentiate the matrix. So that's awesome, and I emphasize again, would have failed horribly if we tried to apply it to a non-diagonal matrix like the one I started with here. Okay, so let's keep this in mind, that when you have a diagonal matrix, life is good. And go back and think about what is e to the a. Well, if we solve the eigenvalue problem for a, then we would end up with a way of diagonalizing a. And you may have forgotten what that means from Math 4a, or maybe you remember. Either way, let me go through it a little bit with this example, and hopefully that'll remind you enough of what you need for this. So first, let's solve the eigenvalue problem for a. Okay, so I've got the eigenvalues -3 and 2, and then these eigenvectors to go with them. So I copied those over, so I'm calling one eigenvalue lambda1 and the corresponding eigenvector v1, and the other one's lambda2 and v2. So here's what is meant when we say that this solving the eigenvalue problem diagonalizes A. If you create a new matrix, let's call it P, whose columns are the eigenvectors, so this matrix, so notice it's built out of v1 for the first column and v2 for the second column. Then, okay, so first of all, if you really fully solved the eigenvalue problem and succeeded in getting a full set of eigenvectors, these should be linearly independent. So P will be an invertible matrix. So there will be a matrix called P inverse, which I will compute here. Okay, so looks like there's a common denominator 5. So how about I do 1/5 and then -1, 2, 2, 1. Okay, so P is invertible, and when you do this, if you conjugate A in this order, if you conjugate your original matrix, so remember it's sort of off screen here, but this was our original matrix A. If you conjugate A using P in this order, then you should get a diagonal matrix. That is the sense in which solving the eigenvalue problem diagonalizes a matrix. And if you really want to get a feel for what's going on, you need to recall how to interpret these matrices as change of basis matrices. So the effect of P would be to take when you apply P to a column vector, it's interpreting the entries of that vector as sort of coefficients in a linear combination of eigenvectors. So it's taking a linear combination of these eigenvectors, which are the columns of P. And then you're applying A to that, and then by applying P inverse afterwards, you're going back and paying attention to what happened to the coefficients. Well, what happened to the coefficients in, let's say C1 V1 plus C2 V2 is that they should get sort of scaled by eigenvalues when you apply your matrix A. So A acts in a diagonal way on coefficients in linear combinations of v1 and v2. To see that, you need to use this change of basis matrix and the change of basis back matrix. Okay, so anyway, that's not too important, just for being able to compute things. So this should be diagonal if we did this right. So let's see. Let me go here and... So all of this stuff you could totally compute by hand and would not take very long, or you can be usable from alpha. It does not have to be Mathematica. I'm just doing it here to save myself effort. So let me call this A, the matrix. Let's call it A, since I'm calling it A up here. And then let's call this matrix P. And then how about P inverse will be the inverse of P. Let me just put a P here. It's probably better. Then if I did this right, then P inverse times A times P. So if you're using Mathematica, then this dot is the way to multiply matrices together. That should be diagonal, and it is. Let me show it in a nice way. It is diagonal. So it's negative 3, 0, 0, 2. All right, and you can see what's on the diagonal, actually. It's showing you exactly the way in which A acts diagonally upon linear combinations of eigenvectors, upon those coefficients in linear combinations of eigenvectors, is that it scales the first coefficient by negative 3 and the second coefficient by 2. So what you're seeing on here is the eigenvalues. Now when you're doing this, pay attention to the order in which you list your eigenvalues. So you can choose any order to begin with, but whatever you choose, stick with it. So here I've chosen for my first eigenvalue negative 3 and the second one 2. In order to keep everything consistent and check my work properly when I'm seeing if this actually works, I need to set up my matrix, change of basis matrix P, in the same order. So the first column is going to be the eigenvector corresponding to the first eigenvalue. The second column, the eigenvector corresponding to the second eigenvalue. All right, so now we have, let me rewrite this. So take this matrix equality and multiply by P on the left and by P inverse on the right. In other words, conjugate in sort of another, do the opposite conjugation as what you're seeing here. So do this. So take what we started with here and then multiply by P on the left, P inverse on the right. Then these are just the identity and these are just the identity, so that cancels, right? And then on the right side of the equation we would have P and this diagonal matrix P inverse. All right, now remember, our goal was actually to compute e to the a, right? E to this matrix. But look, we've written a, by solving the eigenvalue problem for a, we've written a as a conjugate of a diagonal matrix. But e to a conjugate of something equals the conjugate of the e. The exponential of a conjugate equals the conjugate of the exponential. So, e to the a is e to this thing, so e to the conjugate of this diagonal matrix is the conjugate of e to the diagonal matrix, which we know how to compute. So e to a diagonal matrix, that's this matrix. And now it's just a matter of multiplying three matrices together, which is mildly annoying, but we can do it. We can get Mathematica to do it, or Wolfram Alpha or whatever. And that's it. We will have computed the exponential of this matrix. So we will have computed that massive power series, but we'll have gotten around the work by diagonalizing. So let's actually go and get Mathematica to do this. So the answer in the end will be, let me try to show everything on the same screen here. The answer in the end will be P times that matrix there times P inverse. Sorry. E to the minus 3, 0, 0, e to the 2, and apparently it's that. Let me make that look better. Apparently it's that. So all that nonsense that you're seeing there, that is e to the this matrix, 1, 2, 2, negative 2, is that. So what does this achieve? This is telling us if we had x prime equals our original matrix here, 1, 2, 2, minus 2, x, if we had this differential equation, also known as this system, x prime equals x plus 2y, y prime equals 2x minus 2y, then the general solution is well, I guess I didn't put t's there. So the general solution would be e to the ta, e to the t times this matrix. Right, so if let me just call this, I have been calling this a. The general solution would be e to the ta times some vector of constants. That would be the general solution to this system. But I should go back here and insert t's, I think. So if I redo my earlier work, but then stick a t here, how to do this? Maybe I'll keep a being called this, but then I'll stick a t here. Then my eigenvalues just get multiplied by t. So if you just solve the eigenvalue problem for ta, the eigenvalues just got multiplied by t. So these are now the eigenvalues. And then the eigenvectors are the same. You saw those didn't change. And so here you just end up with 3t, right? Okay, so do you see what I'm doing here? I'm saying once I compute this with the ta there, rather than just t. So here I'm solving the eigenvalue problem for ta, and here I'm getting t's. So t times this. I can just pull the t out, actually, right? So then ta is this. So e to the ta is e to this thing here, negative 3t, 2t along the diagonal, which is this, which is this. So this is what I computed over here. It's this big thing. And that matrix, when you apply it to a vector of initial conditions, so let me take this thing that I computed. How about I just copy it from here? Or no, let me take this. So if I take this thing, this is my e to the ta. Now when I apply that to a vector of initial conditions, like let's say 2, 3, then I get a pair of functions which solves this differential equation with the initial conditions I chose. So x of 0 would be 2, and y of 0 would be 3. So there's a lot of 2s and 3s here, so let me put in different numbers like 5 and 7. So let me just convince you, at least in Mathematica, that that works, and that'll also be a check for my own work. So let's define x of t and y of t like this. And then hopefully, first of all, we should have x of 0 be 5 and y of 0 be 7. Yep, x of 0 is 5 and y of 0 is 7, so initial condition satisfied. And then secondly, if I package these together like this, then it should be that when I apply my matrix, this matrix, to them, that should be the same. It should solve the differential equation. So that should be the same as if I took the derivative. So this, this equality, where I take derivatives here, this should be true, right? The derivative should equal the matrix applied to them. So let's test that. Okay, so it gives me a bunch of complicated stuff, but if I simplify it down, it says, yeah, that's actually true. So what we're seeing is e to the ta applied to 5, 7 really is the solution to this that starts at x of 0 equals 5 and y of 0 equals 7. So you already knew how to do this. I just wanted to give you a different perspective and this very cool piece of algebra or calculus or whatever you want to call it, matrix exponentiation. And I think it's really interesting that when we originally started studying this coupled system of differential equations, we found we need to decouple this in order to solve, right? And so solving the eigenvalue problem for the matrix was the way to decouple it. Now with our new fancy exponential way of writing things, where we just say, okay, given this initial value problem, here's the solution. If we actually want to compute this, again, we have to solve the eigenvalue problem for the matrix to actually compute this.